Hello everyone. In this study, we are performing an explicit dynamic crash simulation of a thin-walled steel column using Abaqus. The objective is to evaluate progressive buckling, plastic deformation, and energy absorption characteristic under axial loading, which are very crucial in automotive crashworthiness design. And in this part, I'm creating the steel structural column, which we will be designing in this Abaqus only, as I have not imported the structural member geometry from the step file or any other format. So we are creating a structural column in the space claim manager for this simulation. The model represents a simplified axial crash member, typically used in front or rear crash structures. I have included multiple assumptions like isotropic material behavior, rate independent plasticity, which unless strain the rate is defined, no failure or damaged model in this case. This allows us to isolate deformation and energy absorption mechanisms without introducing additional complexities like fracture. Now, the geometry consists of a straight thin-walled column with uniform cross-section. For discretization, we typically use shell element S4R for thin-walled structures. We have reduced integration with the hourglass control. Shell elements are preferred here due to computational efficiency and their ability to accurately predict or capture the local buckling modes. Now, the material is defined as elastic plastic structural steel. I have included two inputs, which are Young's modulus and Poisson's ratio for elastic response. And the second one is yield stress and plastic hardening curve for post-yield behavior. For crash simulation, accurate plasticity definition is critical because most of the energy absorption occurs in the plastic deformation regime. We are using a dynamic explicit step to solve this problem. Explicit integration is conditionally stable and ideal for highly nonlinear problems involving large deformations, complex contact, and high strain rates. So the stable time increment is governed by the smallest element size and wave speed. So mesh refinement directly affects computational cost. As in, if we are investing in a bit more better hardware, so we can directly use great mesh quality for the mesh refinement, because it will help us affect or change the computational cost. So boundary conditions are defined in on such a basis like the base of the column is fully constrained in all degrees of freedom. The top is subjected to an initial velocity as in the simulating effect. Additionally, contact interactions may be defined. So general contact to handle self-contact during folding. Frictional behavior if required. We will introduce self-contact in particularly because it is important to prevent element interpretation uh, during the collapse. So meshing strategy we will be introducing, in which we will be using refined mesh along the length of the column to capture local buckling modes accurately, and we will include some considerations like element aspect ratio, mesh convergence, and hourglass energy control. We ensure that artificial energy, that is the hourglass energy, remains within the acceptable limits, typically below 5 to 10% of the internal energy, total internal energy. Now, after undergoing the progressive foldings or forming characteristic buckling lobes, this mode of deformation is desirable in crash structures as it maximizes energy absorption. So, key outputs analyzed include von Mises stress distribution, equivalent plastic strain, and the internal energy versus time graph. A study increasing in the internal energy indicates effective energy absorption, while stable folding patterns confirming good structural behavior. So, in conclusion, this simulation demonstrating the importance of controlled buckling in crash-worthy designs. We will retrieve more design improvements in the next part of the video, because it triggers our mechanism to initiate folding, thickness variation, and material optimization. So such simulations are widely used in automotive industry to design safer, lightweight, and energy efficient structures. Thank you so much, and we'll be posting the second part